The next two videos will be about singularities and residues. So this first one is about types of singularities. I think we began to talk about singularities starting from the last video or so. So here we'll talk about types of singularities. First off, a singularity is a point where a complex function is not analytic. So it is what you can call a point of discontinuity for real functions, for instance. So we classify isolated singularities into three types. You have what you call removable singularities, then you have poles, and then you have essential singularities. These are determined using the Laurent series expansion around a point. Okay, so then we go ahead to talk about removable singularities. Um, a singularity at z equals a is removable rather, if the function can be redefined at the point so that it becomes analytic. The equivalent condition is that the Laurent series has no negative powers. So if you have a Laurent series without negative powers, then you have removable singularities at that point. So a removable singularity is just a hole in the function. The function behaves nicely near the point and the limit does exist. So a very good example would be f of z equals sine z over z. At z equals 0, the function is undefined, of course. So at z equals 0, we have um, sine z all over z, that's sine 0 over 0, which is 0 over 0. And because of the 0 under, we have that to be undefined. So at 0 equals, at z equals 0, the function is undefined. Under the series expansion, then, we know that sine z, of course, following Taylor's series, we can easily expand sine z into z minus z cube over 3 factorial plus z raised power 5 over 5 factorial minus z raised power 7 over 7 factorial and so on and so forth. So we can then say that f of z, which is this now, will be all of this expression divided by z. So if that happens, then we can then have z divided by z, that's 1, z cubed divided by z, that is z squared over 6, and so on and so forth. So sine z over z can actually be 1 over z squared over 6. So that means there are no negative powers. So z equals 0 is a removable singularity. So it's actually a removable singularity because by the time we are done, no z here has a negative power. So um, we can then we can define f of 0 to be equal to 1 in that case because we have a removable singularity. Or if you take the limits of this function as z approaches 0, of course you're going to get 1 here. So in this case you say f of 0 is equal to 1. So it looks like we have 1. Okay, we are still talking about removable singularity. So z equals 0 is a removable singularity. So we can plot that here using this code and we get something like this. Okay, so we still get a smooth curve, although z equals 0 is supposed to be a singularity, but it is removable, right? It's just a hole that can be plugged. That's the idea of a removable singularity like that. Then we go ahead to talk about poles. So for poles now, a singularity at z equals a is a pole of order n if f of z is g of z all over z minus a raised power n, where g of a is not equal to 0. So when you evaluate g of z at a, it is not 0. So if this happens, then you can say you have a pole at z equals a pole at z equals a. So the equivalence condition is that the Laurent series has a finite number of negative powers. Finite number of negative powers. Let's see what that looks like. So of course, behavior near a pole then is that as z approaches a, the function tends to infinity. So as z approaches a, this is going to be like 0. So everything divided by 0 is going to be undefined. So for behavior near a pole for a near a pole, right? So this is similar to vertical asymptotes in real analysis. Then talking about types of poles, we then have order 1, which is simple pole, order 2, double pole, order 3, triple pole, order n, pole of order n. So the power you have here determines the number of poles. So we have poles of order n here at z equals a. So example 1 now, f of z equals 1 over z. The Laurent expansion is f of z equals z raised power minus 1. So this one has a single negative power. So this has one negative power. So as a result of that, normally this function is undefined as z equals 0. So we can then say, so z equals 0 is a pole of order 1 because the power is 1. So this is a pole of order 1. So we can visualize this now for 1 over z. So we just define uh, we have all these z, you define that from -1 to 1 in 400 divisions. So z is equal to z such that z must not be equal to 0 because that's a point of that's a point of discontinuity. That's a pole right there. So if you plot that now, you see that there's a jump around z equals 0. There's a jump around. So as this function approaches 0, it just goes off because it doesn't ever reach there. Then from both sides, when the function is approaching 0, it just gets deflected. That's what we talk about asymptotes. So example 2 now, we have f of z equals 1 over z minus 1 cube. So this has a pole of order 3 because of this power. It has a pole of order 3 at z equals 1, 1 being a here. So we can also plot that as we have here. So we have this now. So is a we have a pole at z equals 1 of order 3, a pole of order 3 at z equals 1. That is, then we've talked about essential singularities, removable singularities, sorry, and then we've talked about poles, and now we talk about for removable singularities, right? There are no negative powers of z, but for poles, you have a finite number of negative powers. But then talking about essential singularities, a singularity is essential if the Laurent series has infinitely many negative powers. So you see the trend: removable singularity, no negative power. A pole has a finite number of negative powers, maybe one or two or that. But for essential singularities, you have infinitely many negative powers. The key idea here is that near an essential singularity, the function behaves chaotically. So it takes almost all complex values arbitrarily close to the point. A good example will be f of z equals e raised by 1 over z. So if you expand this, this is e raised by 1 of, you already know e raised by x is 1 plus 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. But in this case now, the x is now 1 over z. So you have 1 plus 1 over z plus 1 over 2 factorial z squared plus 1 over 3 factorial z cubed and all that. There are infinitely many negative powers. So you can see this is z raised by minus 1, raised by minus 2, z raised by minus 3. So infinitely many negative powers. In that case, you can say that z equals 0 because all of these functions are defined at z, are undefined rather, at z equals 0. So z equals 0 is an essential singularity because you have infinitely many negative powers of z in this case. So we can visualize that this way, having defined all that, then we have, so you can see this so there's this interesting behavior you have around here like that. So that's talking about essential singularities. In summary, when you say a singularity is removable, there are no negative powers in the Laurent series and the behavior is finite. Then for a pole, you have finite negative powers, so the behavior goes to infinity. But for essential singularities, you have infinite negative powers and the behavior is chaotic, like what we see around here. So, how do you classify a singularity then? So, first thing you want to do is to check the limit as z approaches a. Okay, if as z approaches a, the function is finite, then it means you have a removable singularity. Step 2, you can then multiply by z minus a raised power n, whatever n you have there. So z minus a raised power n. If the result is finite for n, for some n, it is a pole. Okay, then step 3, otherwise it is an essential singularity. So check as z approaches a, what does the function look like? If it is finite, then you have a removable singularity. If it is not a removable singularity, that is, if the value is undefined, then you now multiply the expression by z minus a raised power n. If the result is finite again for some n, at that point you say it is a pole. But if it is infinite, then it is automatically an essential singularity. So example 1 here, you have f of z equals z squared minus 1 all over z minus 1. So the factor, you can factor this, right? Z squared minus 1 is z minus 1, z plus 1. So z minus 1 cancels out. So f of z can then end up being z plus 1. So the singularity as z equals 1 is removable because you can factor it out like this, or as z approaches 1, you can still you can get the answer is 2 because as z approaches, if you take the limit of z squared over 1, z squared minus 1 rather, all over z minus 1, as z approaches 1, you're going to, of course, if you substitute directly, it's going to be undefined, but you can differentiate using L'Hopital's rule. You get 2z over 1, and then that's 2. Or you can factor out like this. So 1 plus 1 is still 2. So the singularity at z equals 1 is removable because as z approaches 1, this expression is still finite. So example 2 now. Example 2, f of z equals 1 over sine z. So near z equals 0, what happens? Near z equals 0, sine z is approximately z. For instance, if you take the limit of this now, if you take the limit of this expression as z approaches 0, okay? So if you substitute directly, it's going to be like undefined. But if you do L'Hopital's, you get 0 over cos z. And that is going to be 0 in short. So that is defined, right? So sine z, so as z approaches 0, this expression also approaches 0. So in essence, near z equals 0 now, sine z is approximately z also. So we can say that f of z is approximately 1 over z. So this is a simple pole like that. This is a simple pole. So for example 3 now, f of z equals sine 1 over z. So if you expand, sine 1 over z will be, normally you know what the expansion of this would look like. It's an odd function. So you have 1 minus z cube over 3 factorial plus z raised by 5 over factorial minus z raised power 7 over 7 factorial, and so on and so forth. So if you do it for 1 over z, you get 1 over z. If you do it for sine 1 over z, rather, you get 1 over z minus 1 over 3 factorial z cube plus all of that. So there are infinitely many negative powers. So that makes it an essential singularity like that. So intuition summary now tells us that a removable singularity is a whole that can be fixed. A pole is a function that blows up in a predictable way. An essential singularity is a function that behaves wildly and unpredictably. In essence, it is chaotic. So, and then we move on to the practice problems. For each function, classify the singularity at the given point as removable, pole, which is states, and you have to state the order, right? And then you also want to name it if it is an essential singularity. So we have the first 10 here, first 10 questions right here, and then you have the second 10. Can I fit all of that? Yeah, everything can still come in like that. So I'll be solving two of this. Of course, you have extra challenge. I'm solving two questions 2 and 11. Question 2 is this: f of z equals 1 minus cos z over z squared at z equals 0. We want to we want to classify the singularity at the given point, whether to see whether if it is removable pole or essential singularity. And then we'll take question 11 also. So question 11. So we take question yeah, 11, which f of z equals e raised by 1 over z at z equals 0. I think we did this already, but it's okay. I'll just explain it better. So let's take those two, problem 2 and problem 11, and then we call it a date with this particular video. Okay, let me go and switch things up a little bit. Let me go for this one. So we go for problem 2. Problem 2. Problem 2, we have f of z equals 1 minus cos z all over z squared at z equals 0. Of course, you can rewrite this as this, like 1 minus cos z all over z minus 0 all squared. And that is why our a here, that's why z equals a here is actually 0, like that. So if you don't see anything, so a is automatically 0 like that. So with that in place now, we can then go for the steps. So step 1 here. So for step 1, we use series expansion. Use series expansion. So we know already that cos z, if you follow Taylor series, cos z will be 1 minus z squared over 2 factorial plus z raised power 4 over 4 factorial minus 6 z raised power 6 over 6 factorial, and so on and so forth. That's what cos z is. So it means that 1 minus cos z, don't forget up here, we have 1 minus cos z. So 1 minus cos z is equal to 1 minus 1 minus z squared over 2 factorial plus z raised by 4 over 4 factorial minus all that. So that means we have 1 minus 1 plus z squared over 2 factorial minus z raised by 4 over 4 factorial. Because you have minus outside, it changes the sign inside. So plus all the rest now. So in this case, 1 cancels 1. So it means that 1 minus cos z is actually z squared over 2 factorial minus z raised by 4 over 4 factorial plus all that. So it means that there's a possibility of avoiding the z squared. We have z squared under. So we can avoid that. So that tells us that in step 2, we can divide by, in step 2, we can divide by z squared. So we can divide by z squared. So f of z itself then is equal to 1 minus cos z all over z squared. And we know that z is 1 minus cos z, we already got that to be z squared over 2 factorial minus z raised by 4 over 4 factorial. All of this now divided by z squared. This is plus all that now. So that means that f of z is equal to, so we are dividing by z squared, right? So that's like z squared um all over z squared, and then we have the 2 factorial there already, minus z raised by 4 all over z raised by 2, 4 factorial plus every other thing. So we can simplify now. F of z is z squared cancels z squared. So we have 1 over 2 factorial, then minus z squared cancels 2 of this. So we have z squared all over 4 factorial plus all of that. So that means f of z now is equal to 1 over 2 factorial is 2 minus z squared. 4 factorial is 24. So we have 1 over 2 minus z squared all over 24 and all of that. So the next thing is to classify. So we have classification. So for the classification now, so there are no negative powers. At the end of the day, we don't have any negative powers here. So what do we do? That's step 3, by the way. Step 3 is classification. So there are no negative powers of z. There are no negative powers of z. Okay? Therefore, the singularity at z equals 0 is removable. So that's a removable singularity. So the next thing we want to do is to evaluate the value at that point. So step 4 now, value at the point then. So value at the point would have to be, so now talking about limits, as z approaches 0 for 1 minus cos z all over z squared, right? What did we get? We already were able to evaluate this. So this is the expression we have. So that means this is equal to limit at z approaches 0 for all of that ended up as 1 minus 2 1 over 2 rather, minus z squared over 24 plus all of this. So now you can substitute directly. So we have half minus z is 0. So we have 0 squared all over 24 plus all of that. Whatever z we have there to be 0 something. So this goes, and then we have 1 over 2. Okay. So with that now, we can say that so so we define f of 0 equals 1 over 2, basically. So that's the deal with that. Now we move on to the next one, where we talk about problem 11 now. We move on to problem 11. So for problem 11, f of z is equal to e raised by 1 over z at z equals 0. Of course, if you substitute z equals 0 directly, that's e raised by 1 over 1 over, I mean, e raised by 1 over 0, which is e raised by infinity. That will make the whole function undefined. But let's see, is that all we can do? So I then go for step 2. Okay, there's a particular color I've missed after a long while. Let me see. I think this is it. Yeah. So we go for step 2. So for step 1 actually. So we go for step 1. So for step one now, we use series expansion. We use series expansion. So for series expansion now, we have e raised by w equals 1 plus w plus w squared all over 2 factorial uh plus w cube all over 3 factorial. We know all of this normally. So e raised by w equals 1 plus w squared over 2 factorial plus w cube over 3 factorial. And then so we can then say, we are doing this because this is e raised by 1 over z. So but because we already have this now, so if e raised by w is all this, then we can let w to be 1 over z. So if w is 1 over z, right, we can then say that e raised by 1 over z is equal to, so anywhere you see w, put z. So you have 1 plus 1 over z. This is 1 over z, w squared now. So for w squared, we have 1 over z squared, 2 factorial, right? 1 over 2 factorial z squared. Then next, we have plus 1 over 3 factorial z cube plus all of these things like that. Then, if that is the case, we go for step two. So step two now, we analyze powers. Analyze powers. So we know that the expansion, the expansion contains infinitely many negative powers. Infinitely many negative powers. I mean, why is that? We have 1 over z squared, 1 over z cubed. So, 1 over z is z raised by minus 1. 1 over z squared is z raised by minus 2. 1 over z cubed is z raised by minus 3. All right. And so on and so forth. So, infinite. So, and it goes on, it goes on like that. So, what we can then say is that in three, step three, we can then classify. So we can do the classification. We classify, and uh, we can say that since there are infinitely many negative powers, infinitely many negative powers in the Laurent expansion, in the Laurent expansion, the singularity, the singularity at z equals 0 is an essential singularity, is an essential singularity. And that goes. So we go for step four then. So in um, step four, we can just have some behavior insight. Behavior insight. So for the behavior insight, now we can say that near z equals 0, the function near z equals 0, the function does not approach a limit. Okay, the function does not approach a limit. The procedure we said the other time, evaluate at the given point of discontinuity, the point of singularity. If it approaches a finite value, that's a removable singularity. Then the next thing we can do is we multiply by z minus a raised power n. If the answer is still finite, that is a pole. Then if not, it will automatically be an essential singularity. So here, the function does not approach a limit, first of all. Two, the function does not simply it does not simply diverge to infinity, does not simply diverge to infinity. And then next thing is that it takes wildly varying values. The function takes wildly varying values. Wildly varying values. So then we can conclude that this is characteristic. This is characteristic of essential singularities. This characteristic of essential singularities. And with that, we come to the end of all of that. So I'll flash the questions again for you to try your hands on. Um, so practice problem for each function. Classify the singularity at the given point as removable pole, and you need to state the other if it's a pole, and then you have essential singularity. So see questions 1 to 10 and see questions 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed to this channel already, let me know how, let me I thank you very much for doing that, right? If you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join, and that gives you some special privileges like having to see some videos first or seeing some videos exclusively. You can also request for PDF copies of my notes for your personal use. Apart from that, we can hang out online or physically, depending on what works for you. And by in doing that, we can actually discuss whatever interests you on my channel, be it mathematics, data related stuff, scholarships, writing books, whatever. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. So, like, come your way again. Keep doing maths right. Bye.